introduction.
Hello, I'm Rebecca Patterson and this is Rebecca Jordan. We are both students in the course Modeling and Simulation of the Physical World at Olin College of Engineering. Today we are here to address a thermal system that is found right here on Olin campus. Students at the college have noticed a distinct difference in temperature while walking through the buildings on campus. Namely, that the vestibule at the southern entrance of the academic center gets really hot during the first couple months of the school year. This made us wonder, how hot does it really get inside the vestibule, and what temperatures can we expect to experience within the coming months? From here, we reached a specific question. Assuming average monthly conditions of sunlight intensity and temperature, what will the typical equilibrium temperature of the vestibule be for each month? We assumed that this discrepancy in temperature was due to the greenhouse effect on the large window of the southern face of the building, and created our model accordingly.
We modeled the vestibule as a right triangular prism that gains and loses heat energy through two glass windows, one south-facing window to the outdoors and one smaller one to the inside of the academic center. The vestibule begins at the same temperature as the rest of the building and gains heat through solar radiation through the outside window. It can either gain or lose heat energy through both sides of the glass. We then created a differential equation for this model with three terms: the sun's radiation, the heat loss to the outdoors, and the heat loss to the rest of the academic center. The energy gain from the sun is dependent on the shininess of the glass, the reflectivity, or what percentage of the sunlight actually makes it through the glass, the intensity of the sun, which changes based on the season, and the area of the window that the sunlight is passing through. Now, the assumptions we've made in this model introduce some limitations. This is a qualitative, not a quantitative model, so it's going to be better at predicting whether it will feel hot than what the actual exact temperature is. Some of the assumptions we made include the outsides of any walls that aren't made of glass are perfectly insulated, and that the air masses inside the academic center, inside the vestibule, and outside are homogeneous with regards to temperature. Fixing these assumptions would not be within the scope of our project at this time. One other assumption we made is that the outside window would be in full sun for the entire duration of the test. And the sunlight intensity throughout that time would be the average for that month. This, we thought, was a reasonable assumption because our testing period is only 30 minutes.
All right. To see how quickly equilibrium is reached and how different conditions affect it, we ran a few different simulations. For the first one, we set a constant sunlight intensity and varied the outdoor temperature. We assumed, as she said, that the temperature inside of the vestibule started at 70 degrees Fahrenheit, just like the inside of the academic center. As you can see from the results in the graph, higher outdoor temperatures result in higher equilibrium temperatures since heat was gained inside of the room. And then also, accordingly, we have that lower outdoor temperatures cause lower equilibrium temperatures since heat from inside the building is being lost to the outside. For our second test, we set a constant temperature and then we varied the input for the sunlight intensity. As expected, higher sunlight intensities made for higher temperatures inside the vestibule. This is a conclusion we would have logically reached before actually running our simulations. In both cases, it took about 8 minutes for the system to stabilize and the temperature inside the vestibule to stabilize. For our final calculations, we decided that a time span of 30 minutes would be appropriate.
So this chart shows the temperature of the vestibule after it has settled after 30 minutes. So the x-axis is the sun intensity for each month, which you can see in this chart here, and the outside temperature, which ranges from 0 to 100 degrees Fahrenheit. Now, obviously, it's not going to be 100 degrees in January, so we added two black lines to show the average high and low temperature for each month. The area between these lines is our predicted temperature in the vestibule during those months, which ranges from about 60 degrees in the winter to over 100 degrees in the summer. And this varies more than the outside temperature or the sun intensity because those two effects compound. It's hot outside when the sun is intense. And these results actually correspond with what we have seen and felt walking through the vestibule every day for a couple months.
So as Rebecca just said, the results in our graph correspond to the actual behavior of the system as experienced by students here at Owen. If we were to take this model farther, there are definitely steps that we could take in order to increase the accuracy of our results. A couple of such things that we could do would be to actually track how much of the window is exposed to the sun throughout the day, how it changes throughout the day. That way we could pinpoint the difference in temperature throughout the day as well as throughout the year. Other things we could do would be to track the heat being lost through the walls because they are not, in fact, perfectly insulated, and to account for airflow. Also, the exact dimensions of the windowed surface could be found, but since this is a qualitative model rather than a quantitative one, this is not necessary for the accuracy of our results. And with that, we conclude our presentation, and thank you for your time.
Hello, I am Shreya Rangarajan,
I'm Katie Hyde.
and we are first-year Olin students in the modeling and simulation class. So we have noticed that students have been complaining about the temperature in the academic center. So as a result, we came up with the question, what window thermal rating is the most effective for keeping a comfortable academic center temperature? So in order to go about this question, we decided to make a 2D picture. So this shows the academic center in a rectangle form instead of a curvature rectangular prism. So there were 3 flows and 1 stock, so therefore only 1 differential equation. So we modeled our stock and flow diagram. So the stock is the internal energy of the academic center. Our 3 flows were Q dot sun, Q dot window, and Q dot surroundings. So Q dot sun is the energy from the sun. Q dot window was the energy from the window, or energy lost to the window, and Q dot surroundings was the energy lost to the surroundings. So our differential equation at this point was linear, and this would only be the internal energy. So in order to convert it into temperature, we multiplied the linear form by 1 over mass times the specific heat of air. So that came up with our differential equation in terms of temperature. In addition, this is our graph model. So we had 2 graphs. One represented the 100% sunlight exposure through the window, and that shows a nice curve, and it reaches a max temperature at around 100. So then we also decided to make a graph with the different sun angles. So over time, and then at different sun angles, the internal temperature in the academic center reached different temperatures. And obviously at higher sun angles, like 90 degrees, the internal temperature would increase at a lower temperature.
All right. As Shreya said, basically what our model outputs is the maximum temperature that the AC gets to, based on the window the thermal rating and the angle of the sun. So to validate the model, we have a set of 4 graphs that basically show that the model qualitatively works the way we would expect it to. So it's basically saying things like, if the temperature outside is higher than the temperature inside and there's sun coming through the windows, the temperature should increase very quickly. However, if there's something, say, equal outside and inside temperature, but with sun also coming through, the temperature should still increase, but not quite as fast, because you're not getting the increase in temperature from the outside as well, just from the sun. So this also applies to where we could say there is no sun whatsoever. Outside temperature is equal to the inside temperature. That means there should be no change in the inside temperature of the building whatsoever, which is what our model shows. So basically the way this works is that our model is qualitatively validated. So we can say that these behaviors are what we would expect. The temperatures may not be exact, but they are close to what people have experienced in the academic center itself. So our model can say this is the way that the temperature will behave, even though they may not be precise decimal temperature values. So using this model, now that we were able to validate it, we get our results to answer our question, and this graph shows our results. basically what this is saying is we have the window thermal rating down here, the angle of the sun, so from 0 degrees, from right at the horizon, shining all the way through the window, up to no sun whatsoever, and our color rating, this is our temperature scale. The dark red is a higher temperature, whereas the blue is a lower temperature. So basically what this is saying is that when the window thermal rating is very low, so a lot of heat is allowed to come through the window, and the sun angle is also very low, so right by the horizon, all of the sun coming through the windows as well, we have a very, very high temperature. So based on this graph, what we could say is that to improve the problem of the AC getting overheated during the summer, we would want to find the thermal rating that would get us into these blue zones rather than up here by the red. So for future work, we could add things like, say, people in the academic center. So we could add another stock and model the internal body temperature of students studying. This would give us a way to maybe find the perfect, comfortable body temperature and allow the model to decide exactly what thermal rating we would want based on that. Other factors we could put into consideration are the air conditioning. So the AC is obviously constantly trying to cool itself, so we could add that. Doorways, opening and closing and letting heat in and out, as well as adding the top 2 floors.
So in conclusion, some suggestions that we would make in order to cool the academic center would either be to add a thermal resistant sheet, which would block out some of the sunlight, so therefore the internal temperature of the academic center would be a lot cooler, or to add windows with higher thermal ratings, so completely change out the windows. So with that, we conclude our presentation. Thank you.
Here's the setting. You're a hipster. You're sitting down to eat a bowl of soup. It's delicious. It's got some kale broth and quinoa and organic, locally sourced vegetables. But you haven't let it cool because you can't, because you're a hipster, and it's really hot and it burns your tongue. And then you can't taste it, and that's tragic because there's no point if you can't taste it. Luckily, we're here to help you with this model. This model will help you find the ideal cool down rate for your given amount of time that you have to eat the soup, and find the ideal bowl so that you can eat your soup while it's still hot and it'll be pleasant the entire time. We were looking at the radius to height ratio for a bowl and a mug, each of which would hold 473 cubic centimeters, which is about 2 cups of soup. In order to model this situation, we had to make some assumptions. So we assumed that because the properties of soup, such as density and thermal properties, are pretty close to those of water, that we would use water for this iteration. We set some initial temperatures of the soup and the walls of the bowl. We set the constant volume, so there's no one eating this soup, but that could be in a future iteration. And we have a 345 to 336 Kelvin temperature range for the soup to be pleasant to eat. And therefore, our initial temperature is 345 Kelvin. And we also set some parameters for the vessels themselves. So they are 0.75 centimeters thick, and we have some radius ranges for the bowl, 3 to 6 centimeter radius, and for the mug, 1.8 to 5.2 centimeter radius.
So another simplification that we made is that we didn't actually look at the gradient temperature of the soup. We treated it as one main temperature in order to get that 345 degree to 336 degree range. And clearly that's the most important temperature in our model, but we wanted to make sure that we got that temperature right. So we decided to keep track of 2 other temperatures in the model as well. And those are the inner layer of the bowl and the layer of the bowl that touches the outside air, so that interacts with the environment. And so we used 3 different sets of differential equations to model this. We used convection to show the loss of heat energy from the soup to the air and the loss of heat energy from the outside layer of the bowl to the air, and we used conduction equations to model the temperature change or the change in heat energy within the bowl in that inner layer that we were talking about. So the first step in verifying this model was to actually make sure that it exhibited behavior that we expected it to for the 3 different temperatures that we're following. And these are the two graphs for a given radius and height ratio for the spherical cap bowl and the cylindrical mug. And as we can see, the three temperatures that we model change at a very similar rate, and they all go downwards as we would expect them to over a 60-minute time period. The next step, of course, after we show that this exhibits behavior we would expect, is to make sure that it's actually realistic behavior. And so we took a real world bowl and a real world mug, and we put hot water in it, and we measured the temperature change over a given period of time, which was 25 minutes in our case. And as we can see, the orange line is the measured data, and the blue line in both of these instances is the modeled data for all of the parameters of our bowl and mug that we used for this validation model. And as we can see, they're very close, so they're within the error margins that we would hope our model would have, but there is still some variation. And we were talking about it, and we decided that the variation was probably due to the fact that the bowl was not a perfect spherical cap and the mug was not a perfect cylinder. The mug, for instance, had a handle, which would throw off some of our surface area equations that our differential equations were dependent on. Additionally, there were probably some environmental factors that made a difference, changing room temperatures. Since we were doing it in a kitchen, there were lots of people milling around, so there were some other factors that would account for this difference as well. So the next step, of course, was to actually generate our punchline graph, the whole point of this model. On the y-axis is cooling time in minutes, and on the x-axis is the ratio of radius to height for the mugs and the bowls. The top line, the blue line, is for the cylindrical mug, and the green line, the bottom line, is for the spherical cap bowl. This graph makes a lot of sense because if you think about it, a bowl will take much less time to cool soup than a sphere or a cylindrical mug would, because there's more surface area of the soup exposed to air than there is of the soup exposed to the actual vessel, and heat dissipates much more quickly through the air. However, some limitations of this model are that we have this huge span of time ranges in the middle here where there's no vessel that you can eat your soup in if you say only have 30 minutes or you only have 20 minutes to eat your soup. So that's probably due to the strict parameter limitations that we had as assumptions at the beginning, because we have very strict radius limitations. So if we had a more expansive range of radii to height ratios, we would probably be able to model some of this intermediate behavior, and it would be less of a limitation.
So in future iterations, we have a few ideas about how we could continue using this model. First of all, we didn't have anyone eating the soup, which is kind of important. So we would need to add in a volume change and an energy change from someone taking slurps of soup. And we've actually talked about some different slurp rates for different amounts of time that you have. So if you're a hurried eater, or an eater that's just on a date, or an eater that has a lot of time and is distracted. We also were thinking about different thicknesses and materials and properties of vessels and parameters relating to the environment. And also we could make the soup more complicated. Right now it's just water. We could add in things like, what if there were potatoes in the soup that were retaining heat, or what if the soup is thicker or less thick, and that would affect the cool down rate of the soup.